All right, hello Sydney. We are finishing up activity 6. And we just determined that some of the heptagons we built, or all of them, like this one here, when we looked at the interior angles based on page 1, we got a sum of 900 degrees for a heptagon. All right, octagon. Did anyone get that one?
1080.
1080, that's correct. And a 9-sided is called a nonagon.
1260.
And you got 1260 on yours?
Yes.
Okay. So I'm just going to show you something cool here. Slight diversion that's related more to the next project, but kind of to this one. I have a link out to a file I created for Geogebra here that if anyone goes there, it will take you to the Geogebra app, which is a little bit different than the Geogebra software online. And so it gives you this pentagon that I built. And on the side, I have angles in here, and the angles have names: alpha, beta, gamma, delta, and epsilon. So the system Geogebra likes to choose Greek letters for the angle names. And I just said S, add up alpha, beta, gamma, delta, and epsilon. And that's where the 540 right here comes from. It's the sum of those angles. But watch this. If I just grab one of these points and move it, it changes other angles. But guess what happens to the interior sum? It stays the same, yeah. So as this shrinks, those guys had to grow to compensate. If I take this and I push it inside, the other ones have to shrink to compensate. Okay. So this is still a pentagon. The sum of the angles is still 540. Okay. And all I'm telling the computer is to display the sum of those three. So building this was a little bit tricky. It's not too hard, but I'm not going to have you guys do that right there. But I'll show you an easy use of Geogebra. So I'm going to go to the Geogebra homepage, and I want to do geometry. And they've got some basic tools here where you can put a point, a line segment, a line, a polygon, where you just like draw a polygon. Going back to where you started completes it. More tools gives me a whole bunch of other options. And under polygon, I can draw any old polygon, or I can make a regular polygon. So let's see, which was the last one we were looking at? A nonagon, the 9-sided. So to draw a regular polygon, you have to give it 2 points to start with. And then it says, okay, that's how long a side is. How many sides do you want? And I can say, oh, I want 9 sides, please. Hit OK. So here it's a regular nonagon. Oops. Oh, cancel. Sorry. I always forget that if you want to move stuff around, you got to switch to the move tool. Otherwise, it tries to keep doing the last thing you did. Another cool thing is Geogebra will automatically measure angles for you. So one way to measure an angle is you click the angle measure tool, and then you click points with the middle point has to be the one you're measuring. So if I want to know the measure of this angle, I would click A, I, and then H. And I'll say, oh, by the way, that's 140. Even cooler than that, there's undo right there. Undo. If I click the angle measure tool and then I click on the polygon instead of 3 points, it'll measure every angle. So here it's saying in an onagon, in a regular one, each angle is going to measure 140 degrees. So anybody with a calculator, what's 9 times 140? 1260, which is just what we came up with before. Okay. So the trick here is, can we then do we have a pattern to the numbers here as we go from 3 sides to 4 sides to 5 to 6? So can somebody tell me anything about this pattern here? Yeah, each time we add a side, we get 180 degrees more.
Or it's the number of sides times 60.
Ooh, the number of sides times
right?
60. So let's see, 6.
Right.
Well, 6 times 6 would be 360, so that you're close.
No, I had it a minute ago. Now my brain just isn't working.
So would you agree I'm adding 180 over and over again? So what's repeated addition? Yeah, so the formula has to have something to do with 180 times something. And the question is, what do I multiply? Well, if I take 3 sides, what times 180 equals 180? 1. Okay. If I have 4 sides, what times 180 is 360? 2. So this right here is different color. Let's try blue. So this one right here is blue. Come on. There we go. There we go. 1 times 180. This one right here is 2 times 180. This 540 is 3 times 180. So how do I get from the number of sides to the multiple? Yeah, it's n minus 2, it turns out. N minus 2. Yeah, so 180 is the key. Does anybody think of a reason 180 is special in geometry? There's a few reasons.
It's a straight line.
A straight line is 180 degrees. Any other thoughts about 180 degrees?
Triangle.
Interior angle of a triangle. Yeah, okay. So on a piece of paper, draw a hexagon. I don't care, not a hexagon, a pentagon. I don't care if it's concave or convex, but everybody draw your own pentagon. Doesn't have to be regular, but it can be. Just draw a pentagon. So 1, 2, 3, 4, 5 sides. That's a possible pentagon. It's kind of like a funky tooth. Maybe it's more like a house. There's another pentagon. Okay, next, pick a single vertex, any vertex, just one of them though. So on my first one, I'm going to pick this vertex right there. My second one, I'm going to pick that vertex right there. So now what I'm going to do is from that vertex, I'm going to connect it to vertices it's not already connected to. So I'm going to make some diagonals. So I could make a diagonal from there way over here. Or I could go from there way over here. And I could only draw 2. Does that sound right? From here, I could draw 1, 2 diagonals. And we figured that out before with Taylor's question. In a pentagon, we can get 2 diagonals from any particular vertex. So what happened when we did that for one vertex? What happened inside of our pentagons? We made 3 triangles. Triangle number 1, triangle number 2, triangle number 3. Triangle number 1, triangle number 2, triangle number 3. And what those triangles do for us, let's use green, is they basically build the angles of the pentagon inside. So this triangle right here has 1, 2, 3 angles. And what are those angles going to add up to? 180 degrees. Triangle number 2 has this angle, and that angle. And those angles add up to 180 degrees. And triangle number 3 gives us this angle, and that angle, which is another 180 degrees. Now, I got a bonus out of those 3 180s because what it gave me was let's say this is the first angle of my pentagon. Here's the second, there's the third, there's the fourth, and there's the fifth. It gave me all of the interior angles of the pentagon. So what we did is we dissected the pentagon with triangles. And how many triangles do you need to dissect a pentagon? 3 of them. No matter what pentagon we drew, right? I'm sure every one of us drew a slightly different pentagon. It took 3 triangles. Each of those triangles has 180 degrees interior, and 3 times 180 gives us that 540 that we found before for the pentagon. So it looks like for any pentagon we draw, doesn't matter whether it's concave or convex, we're going to have a sum for the interior angles of 540, which is pretty awesome. So next, draw yourselves a hexagon and see if you can dissect a hexagon with triangles. See what happens. Any old hexagon you want. I'm going to draw a GeoGebra for fun this time. GeoGebra, may I have a new screen? Let's see, how do I do that? New. Let's save that one. That's okay. I'm going to save you. Hexagon step. 1, 2, 3, 4. Oh, 5, 6. So there's my hexagon. And then inside of it, see if I pick on this one right here, I can make 1 triangle, 2 triangles, 3 triangles. I get exactly 4 triangles when I dissect from 1 vertex. So 4 triangles is going to be 4 times 180. And on a good day, 4 times 180 is 720. Is that what we had in our table? 180, 180, 180, 180. And because there's no overlap, they build all of the angles without missing anything, without overcounting anything. We get exactly all the angles we want out of there. So it's a slightly different way to look at why a particular polygon is going to have, 180 times n minus 2. Because in any polygon, you can dissect it using triangles. You're always going to get n minus 2 triangles. A triangle has 180 degrees in it. It's kind of nice. Wow, this is a fun day, wasn't it? Sort of, kind of. I love playing with these.
Understand what the difference is. It says if polygon is regular, how would you determine it?
Okay.
Wouldn't it be the same?
So, good question. So if a polygon is regular, how would you determine it? So let's see. I need a new screen, please. Geogebra. All right, so I'm going to use the regular polygon tool, and I'm going to pick on, let's say, a hexagon. All right, so there's a regular hexagon right there. Let me put it in my screen. Oops. Programs. There we go. All right, so here's a regular hexagon, for example, and we want to come up with the measure of an interior angle right here. So one thing we know, if we're in a regular one, all of these angles have exactly the same measure. Right? So we can call this measure x, for example. So I know the sum of the interior angles has to equal 6x. What else?
So would you just use the 180?
So let me double check the question, make sure I'm on the right track. Back. This was on the activity, right? Okay, if a polygon is regular, how would you determine the measure of each interior angle? Okay. Yeah. So we already know we have a formula for the sum that says it's going to be 180, in this case, times 6 minus 2, or 180 times 4. That's an x on times, this is a times on an x. So putting those together, I know that 6x has to equal 180 times 4, which is what, 720. So I could use a little bit of algebra.
Using that formula and
Dividing by the number of angles. Or, yeah, because it's regular, it's equiangular, is what I'm thinking there. $12? 120, sorry. Would be the measure of each angle.
So would a formula be 180 times n minus 2 over n?
So if you wanted, yeah, so if it's regular and you want one interior angle, colors, we know that the total is 180 times n minus 2 If we divide by the number of angles, then that'll give us a single angle. All right, I think this is a good stopping point. I just want to point out something about the next activity we'll do in class. We get to get a little more physical on that one. So on that one, I'm going to, instead of playing with the toys, I'm going to force you to play with the geometry software. And there's a whole bunch of them out there. I'm picking GeoGebra because it's been around for a long time. It's very well developed, and I'm used to it. So I'm a little biased in that regard. And I pre-made a file to get you started with GeoGebra. I'll guide you through making a couple of other GeoGebra files in the next class. But the funner part of this is we can do this project without GeoGebra with chalk or tape, building the human-sized polygons, like polygons we could hang out in. And then what we're going to do is play around by walking the edges of polygons to figure out what's going on with their angles. And we can actually do this for activity 7 and activity 8. There's some fun stuff there. But we're going to start with a pentagon. And so my instructions here, does anyone know they're not going to be here next class? Probably going to be here? Okay. Okay. Yeah, so we'll do this together then, but if you're not here, I tried to give instructions here, and I'll make a little video next class about what I mean if this isn't clear, about building walking pentagons to help figure out what's going on with their angles. All right, that's it for now. If you want to take any of these toys home with you, please. I got some baggies up here, help yourself. But I think you probably don't need them because I think we finished up this activity for the most part.
Oh.